Okay, now I will get started and I will record this session. So hopefully everybody will see my recording. I posted on Canvas. Now we are at chapter 3 for today. Chapter 3, we will cover 6 topics. I will go through every topic. And I will also give a couple of demos about the topic we're going to cover. So give you an idea how everything works in real world. So we will get started with the first topic. It will be the concepts of AM modulation. So the subject for chapter 3 will be AM, amplitude modulation. And what exactly is AM modulation? It's a voice signal. Usually it's voice because we are talking about communication. We want to broadcast a voice. So the voice will change the the amplitude of your carrier. So this will be an AM, typical AM. And that sign will be the modulating signal. And the modulating signal, the high frequency will be the carrier. So this will be the carrier. And the envelope will be the modulating signal. So if I go back to my demo, let's see what a real signal looks like, real AM modulation signal. Hello, actually, I already started recording, so.
Your office hours Zoom, I couldn't get in. I was wondering why.
Office hours? Today?
Yeah, earlier. Anyway, that's irrelevant.
Let me give you a demo. We are talking about the AM modulation. So we are looking at a real AM signal. Let's do a simple one. So this, I really like this setup. This setup is actually actual signal. It's actual instrument. The only difference is the output is on a computer monitor. So it's a really excellent way to do this Zoom meeting because we can share this output. So let me change the wave gen. The wave will be the AM signal. The modulating will be 1 kilohertz. Not 1 hertz, 1 K. So we will use 1000 hertz to modulate 50,000 hertz sine. So let's look at the results. No. All right, we will use 1000 hertz sine to modulate 50,000 hertz sine. So let's look at what AM looks like. So this is what AM looks like. Let's get a little bit closer. So that's what AM looks like. I changed to 20K. So the carrier right now is 20,000 hertz. So I'm slow down my carrier a little bit. And now let's look at so that's what AM looks like. So also I can change how much I modulate. That's our second topic. So I change it to 50%. All right. Now it's 50% modulation. So 1000 hertz sine modulate a 20,000 hertz sine. So I can also change the modulation. This is our second topic. Second subject is a modulating index. So if you go back to our signal generator, right now we can change it to, for example, 20% modulation index. And let's look at what it looks like for 20%. So that's 20% modulation index. Notice the amplitude varies only 20%. So this percentage modulation or modulation index, whatever name you want to call, percentage modulation means how much percent the amplitude varies. The extreme case, let's go to the extreme, is 100%. So that's the maximum modulation, 100%. And let's look at 100%. So this is the maximum modulation, 100% modulation. So that's what it looks like, 100% modulation. And that's maximum modulation. What happens if you keep increase the intensity of your modulating signal, this 1000 hertz, you will over-modulate. So let's look at what the over-modulation means. Let's see, the modulation index changed to 200%. Now we are over-modulating. So yeah, that's what over-modulation looks like. So right here, it's called over-modulation. So you are go to the negative region. So your sine is right here. You over-modulate. So when you over-modulate, when the AM receiver receive your signal, the receiver will detect the envelope. So obviously you got distortion here because the original signal is sine. When you received, you flip over this negative to positive. So the sine starts from here, ended to here. That's the 1K sine. That's, for example, human voice. If you over-modulate, you got distortion, and you get unable to hear the original voice. You may not be able to understand what the radio station is talking about. So that's our first and the second topic. The second topic is the modulating index. And it has to be keep under 100. The maximum is 100, and we should keep it under 100. Well, let's change it to 100. All right. That's the maximum amount of modulation. So when the receiver receives this AM broadcast, the receiver will detect the upper envelope which is the original sign right here. So there's no distortion happens. Of course, you might accidentally overmodulate over here. So let's keep it, for example, 80%. All right. So now we got 80%. That's a little bit better because potentially you avoid accidentally overmodulate. When your signal gets stronger, you cross over to the negative part. So 80% modulation. It's a perfect sign on the envelope. We noticed we also have the sign on the bottom half envelope. So the AM receiver generally pick the upper half. It doesn't matter if the receiver pick the lower half, it's also okay. But so either upper or lower half. So that is the first two topic. The third topic number 3 for today will be the frequency domain. So if you look at this signal, we are looking at the AM broadcast signal at the time domain. In many occasions for analyze or study communication system, we also want to look at the same signal, look at the spectrums. So that means look at the same signal in frequency domain. So how do we do it? Actually, with this system, it's very easy. All we need, before you need a spectrum analyzer. Fortunately, we have it right here. So this is the spectrum analyzer, and it will find the spectrum of let me make the spectrum analyzer works good. So this is how spectrum analyzer works. On the upper half is time domain, which we kind of compressed. So you still can look at your original AM signal, which is 80% modulation. So modulation index is 80%. We can change it to 100%. Let's change to 100%. So now we got 100% modulation, and so the upper half is 100% modulation on AM, and the bottom half is the spectrum. Oh, did I share? Yeah, I think I'm sharing this screen. Okay. So bottom half will be the spectrum. Let me reshare it. I just make sure I'm sharing this for you. All right. So the upper half is time domain. The bottom half is frequency domain. Notice in frequency domain there are 3 components. Component number 1, the biggest one, the bigger one, is the carrier. Why? Because if you look at the carrier frequency is 20,000 hertz. So if you look at the spectrum, that 20,000 hertz energy is right here. So this is the carrier. So the AM signal, the carrier is the strongest signal in frequency domain component. So 20,000 hertz, that will be the first component. Then we have 21K and 19K. So we have 2 components. This is called upper side band, Ssb. So we got the Ssb upper side band. We also got the lower side, which is at 19. So it's 20 plus 1K, 20 subtract 1K. The reason it's 1K apart is because the modulating signal is 1K. So if I change my modulating signal to 2K, if you look at the spectrum, Yeah, it's 2K now. Now everything is the same. The only changes is the upper side band now is 22K. Lower side will be 18K. So I can change it again to 500 Hertz. So if I change it to 500 Hertz, now it's getting closer and closer. So everything else the same. It's original carrier, still at 20K. So carrier never changed, it's 20K. The modulating signal upper side will be carrier plus the modulating frequency, which is 500. 20K plus 500. So right now we have 20.5. The lower side will be 20, subtract 500, will be 18.5K. So let's move it back to 1K, the modulating signal. So now 1K being 1K, and this is 21K, this is 19K. So upper side and lower side. So that will be our third topic. Well, most radios do not send out. Most radios do not send out the psi. So right now we are just sending out psi. So most radios, this will be the human voice. So when we talk about human voice, we are talking about not a single frequency. For example, human voice, we are talking about 300 Hertz to 4,000 Hertz. So 300 Hertz one. Let me move over to my other camera. So this is a carrier, and if your modulating signal has only one frequency, 20K, then you have 21K and 19K. So that's all you have if the modulating signal is only 1K. So what happens if your modulating signal, is 1K, your carrier 20K, in frequency domain, you have carrier upper side, lower side band. Upper side is 1K above, lower side is 1K below. So that's all three components of your AM signal. But what happens if your modulating signal is not a single frequency? Instead of a continuous frequency of 300 Hertz to 4,000 Hertz, for example, human voice. So now 20K is still the same. So this is a carrier, 20K. And then you will have not a single component like previously. You will have anywhere from 300 Hertz to 4,000 Hertz above. So you will have this band. So this is called the upper side band. So upper side band, where the upper side band start? It started with 2,000.3K, right? That's 300K above carrier. It will end it with 224K. So this is the frequency range of upper side band. How about lower side band? Lower side band will be 300 Hertz below and 4K below. So what is 4K below? 16K. 4K below 20K. And what is 300 Hertz below? It will be 19.7K. So this will be the lower side band. The lower side band will be 16K to almost 20K. It's 0.3K below 20. Upper side will be 0.3K above 20 and ended with 24K. So this will be your complete spectrum of a signal, AM signal, if we are using human voice to modulate. That's a typical AM station, so AM broadcast station. So if you're listening to an AM station, this is what your received signal looks like in frequency domain. And each AM station has a bandwidth of 10K hertz. 10K hertz. So that means it's enough space for human voice, which is 4K above, because this is a 5K above, this is 25K. So it ended at 24K, so it's okay because every station has 5K above and 5K below. That's the spectrum for AM station, because you have this 10K and human voice can be broadcast, send it out, enough bandwidth to broadcast human voice. So let's try to have that demo here. First, we need a human voice. Let me change my share to. I recorded a human piece of the music. So all I'm going to do is import. This is the music I recorded before the class, so I will open it. So once it's opened, I will use this recorded 3 minutes song. I remember 3 minutes, but so I will use actual music, actual song, actual music to modulate this carrier, which is 20K. And let's look at the AM signal in both time and frequency domain. That's the idea. So we will be looking at a real signal from a real AM station, for example. This AM station now will broadcast a pre-recorded song, a pre-recorded track, a music track. The carrier frequency will be 20K hertz, 20,000 hertz. So now the song is loaded up. This music is right here. So I will just say, okay. I will use this to modulate. So a modulation index, I will change it to 90%, 80%. So now I'm ready. So the wave generating part is ready. Now I'm on the, okay, this is what AM signal looks like. Now we are looking at the AM station in time domain. So notice the upper envelope will be the music. So does the lower envelope. So the receiver can either use the upper envelope or lower envelope, you will hear the same music. So upper envelope or lower envelope, this will be the same music. That's your AM station in time domain. Now what I want to look at is what about the frequency domain. The carrier is 20,000 and you have some voice. Suppose goes from 300 to 4,000 hertz, right? 300 to 4,000 hertz. So let's look at the this will be the bottom part. The yellow is what this AM station looks like. The top half is the time domain. The bottom half is the frequency domain. Notice it has a strong energy at 20K. And then if you noticed here, from 16K to 24K, you have some activities from 16K, even here, even here. So after modulation, our AM signal in frequency domain this is the upper sideband from started from 20K, ended at 24K. So this will be your upper sideband. And that will be your lower sideband. Notice our modulator actually cross over to after 24K. Obviously, if this is a real AM station, you need to do a filter. What do we mean filter? That means you need to remove anything below 15K, anything above 24K, 25K. So that's what this part comes into play. So we will add a filter. We will add a filter here. So the filter, we will do a band pass filter. The band pass filter started with 15K, ended with 25K. So with this band pass filter added, so this is what happens after the filtering. This is ideal because we remove anything below 15K. We also remove anything above 25K. So if you look closer, you see, even closer. So this will be the spectrum of an AM station. It will start at 25K, 15K, 15. From 15 to 20 is lower sideband, The frequency always changes because we are talking about the dynamic sound. So it's always changing, but it's never reached over 15K. So your neighbor will be happy. It's like you're building your fence. You don't want to build a fence on your neighbor's yard. So anything below 15 is another station. Anything above 25 is also a different station. So that is your spectrum, and your voice or your music, whatever you want to broadcast, is modulating this 20K carrier. So your station starts from 15 and ended with 25K. So this is the AM. And now, of course, we can look at our AM in spectrum in time domain. So this is what the AM broadcast looks like in real time. That will be the signal goes to the antenna. And this is called RF signal. So this signal will send out to the antenna. The antenna the radio will depend on the power, how powerful your stations are. It can travel, and also depend on the carrier frequency. It can travel, in the most extreme case, thousands of miles, or even millions of miles. If you point your antenna towards sky in certain frequency, it can travel forever, outer space. So if you have enough power, the radio signal will keep travel at the speed of light. And of course, the receiver will receive this signal and will amplify it and pick either the upper envelope or lower envelope and send that signal to the speaker. So you will hear the AM broadcast. So that's the whole system. And this is the AM signal in time and in frequency domain. So that's a frequency domain. Okay, that's our third topic. The fourth topic is AM power. If you notice, when you look at your AM station, notice the 20K is really strong, the 20K region. So let's do some math analysis. It turned out what you observed here, mathematically, it turned out if the carrier is 1,000 watts, if the carrier is 1,000 watts, so that's the peak. This guy right here is 1,000 watts. Well, if the carrier, we have a AM station, so the carrier we send out 1,000 watts, so it will travel maybe hundreds or if not thousands of miles. So this 1,000 watts carrier, but unfortunately, carrier do not carry any information. So in this particular case, that 1,000 watts is pure waste of energy. But it's necessary waste because we are using AM system. You have to have the carrier because that's what completed AM signal looks like, has a strong carrier. So when you broadcast your AM antenna, the majority of the energy, that 1,000 watts, is energy wasted. So what about all the energies of upper sideband and the lower sideband? It turned out it depends on the modulating index. So if we modulate If we modulate 100%, let me share my camera. So this 1,000 watts will be the carrier. So the carrier will be 1,000 watts, for example. So how much is on the upper side and lower side? It turned out it depends on the modulating index. If we have 100% modulation, it turned out the maximum power for upper sideband, Ssb, the maximum power for Ssb is 250 watts. So does maximum lower sideband is 250 watts. So this is just a little bit of math. I just provide the results. And the 100% modulation, only 250 watts is on upper sideband. Another 250 is lower sideband. And if the carrier is 100 watts. So what does that imply? This add together is 500 watts. That means the total broadcasting power will be 1,000 plus 500. So the total power transmitted will be 1,500 watts. Total power is 15 watts. Only 1/3 is information. 2/3 are waste. So the conclusion is the maximum amount of power for information in an AM system is only 33%. 33% is the modulating signal. 67% is wasted. Because the 67% is the strong carrier, which must be there. in order for this AM system to work. So 2/3 of waste. So if we switch over to my demo, it's proof. So if you look at this system, the spectrum, the biggest one is 2000 Hertz right here, right in the middle, 2000 Hertz. And then the rest is kind of small. So the total power of all those add together, it doesn't mean it's a single one. All those small, let's zoom in a little bit. All those little guys, which are moving up and down, flashing, all those little guys, all of them add together. And also the upper side, all those add together is 2/3. And yeah, all these add together plus upper side plus lower side, all of them add together. If you look at it, all of these little guys add together is only 2/3 of the total. And this top guy, 1/3 of the total. All the little guys add together is 1/3 of the total. This carrier 20K is 2/3 of the total energy. So a typical AM station, the maximum efficiency is 2/3, 1/3, 1/3. 2/3 is waste. 2/3 is waste. That waste energy. So AM obviously is not a good technology, but it's the oldest technology. It's still used today. So if you drive in, you have your choice of AM or FM station. It's still analog, still the way it was 50 years ago, or even maybe 100 years ago. Still the same AM technology used today. That's probably the only technology, AM, FM, we didn't convert to digital. Everything else, the technology changes overnight. Everything else is changing rapidly. This AM system still stays for today, even today. So if AM is such a terrible idea, so people began to think about ways to improve. So one way to improve it is called remove the carrier, right? One obvious choice we want to have is what happened if we remove our carrier. So that's our topic number 5. So that's a modified AM system. There are 2 modified. The first is called the DSB. For DSB, what we meant is we just remove the carrier. So this is the upper side, this is the lower side. And what happens if we just remove that carrier and we just transmit these 2 energy? That should be great because that is 2/3 of the energy. So if we remove this, our previously 1050 watts, that's the total broadcasting power, 1050 watts. If I remove the carrier, that's 1000 watts. Now my AM station, now we do not call AM station, we call it DSB, double sideband. My DSB broadcast will only broadcast 500 watts. So that will save huge amount of energy bill. You don't have to waste that 1000 watts. You only transmit. So your transmitter is only broadcasting 500 watts. So that's DSB, double sideband DSB. All right, if we can use DSB, and also we noticed the DSB, this is the DSB signal. So that's upper sideband, lower sideband, and that's my DSB. And we notice the upper side, lower side is identical. Mirror image, that's the center. So it turned out we don't even need both sideband. We only need one of them. We only need to send out one of them. So if this is 250 watts, so from AM is 1,500 watts, that's AM. DSB, we only need 500 watts. Transmitter, we only need send out 500 watts. When we shift it to Ssb, only 250 watts is needed to send out the same strength of signals. So we can either pick the upper side or lower side. It doesn't matter. So let's assume we pick the upper side band. So this is called upper side band Ssb. Of course, we can use alternatively, we can have lower side band Ssb. So there's two Ssbs. When you receive a Ssb signal, the receiver have to know it's upper side or lower side Ssb in order to demodulate. So obviously, this is the best. You can, for example, go 100 miles with the 250 watts transmitter, or 500 miles with this 250 watts transmitter. To achieve the same range using DSB, the transmitter have to transmit 500 watts to reach 500 miles to reach the same destination. Ssb 250, DSB 500, reach the same destination. AM 1,500. So obviously this is the worst. Although we achieve exactly the same thing, transmit some human voice communicating 500 miles to the destination. AM, traditional AM need 1,500, DSB need 500, Ssb only need 250 watts because we only transmitting one sideband, which is in this particular case will be 250 watts. So Ssb obviously is the best. Of course, this is the transmitter. On the receiving side, AM is the easy to receive. DSB is a medium, is okay. This is hard. It is difficult to demodulate Ssb. So you gain some, you lose some. So AM, although we're wasting a lot of energy, but the receiver can very easily receive the modulating signal. For DSB, it's a medium. Yeah. It's not as difficult as the most difficult is Ssb. Ssb, the receiver is most complicated. You need extra component, extra circuit to demodulate this either upper side or lower side band Ssb signal. So when we talk about the receivers, we will talk about this part. So depend on your application. A lot of cases, if energy saving is the most important, we choose Ssb. That is the case for mobile application. So handheld device using batteries to power up the transmitter. So you want to conserve energy. You don't want to use this method because your battery will last. Will be out of power very quickly. In this case, if the battery will last how many times? 6 times longer than AM. That's the same battery lasts 6 times longer because power is only 1/6 of AM. So So this is 1/3 of the power. This is 100%, 1/3. This is 1/6 of the power. Compared with this 100 power AM. So can we generate a Ssb? Yes, we can do it here. So let's go to my demo. By the way, I have said this again and again. The demo is I'm using this. All the demo came from here. So everything is going on right here. And this is the best technology for today's Zoom education in case of electronics, because all the instrument is built inside. And the only thing missing is the display, which is on computer. So all the instrument, the result is on computer. That's why I can show you guys the results. So let's look at what will be the results of Ssb. Let's stop sharing this camera. Put up my instrument panel. So now this is the AM. So AM station. That's your AM in time domain. And this will be signal sent out to the antenna. Huge waste of energy, but we're still using this technology. So what happens if I want to remove the carrier? So remove this guy right in the middle, the strong guy in the middle. I want to remove the 20K. So in order to remove that 20K, what I'm going to do is goes to this filter again. Instead of bandpass filter, I want to band stop. So band stop, I will say 19.5K. And 20.5K. So I will stop anything in between. So basically, I will remove 20K. Let's see what happens. Yeah, the result is right here. So notice this big guy right in the middle, it's all disappeared because I filter it out. All it's left is the upper side and lower side. The carrier is removed. So it used to have a very strong carrier right here at 20K. After the filter, this filter can be digital. Right now, this filter is a digital filter. I'm doing the filtering on my computer. In the old days, before computer, this will be an analog filter. So we will build an analog filter. And after pass through this analog filter trap, usually called a trap. So it will trap the 20K. So let's look at this filter. This filter is a Chebyshev. This is the most common classic filter. So Chebyshev filter, we can build analog, we can build digital. Right now it's digital. So it's the order, we can increase the order. Anywhere from the higher the order, the more complicated the filter will be. In case of analog, the more circuits you have to add. In case of digital, the more computing power you have to have in order to accomplish the filter. So this right now, the maximum order is 16th order. So now we can do a 16th order. That means a more deep compression of 20K carrier. So we didn't really see the difference because previously it's 12th order. It's already pretty good. What we also can change is how close we are to the 20K. For example, we can say 9 and 20. So now this filter is really sharp. It's only started at 19.9K, ended at 20.1K. So that's what happened. Yeah, now this is a better filter because it will keep more of upper side and lower side band signal. still the 20K is missing. You see, notice that if you look at here, the 20K, which is the carrier, is still missing, but we have more of upper side and lower side kept, because if you filter the previous one, it's remove a little bit of modulating. That means your voice will be distorted a little bit. This is a better filter. So this filter only 0.1K. The band stop the stopping band will be 0.1K below and 0.1K above the 20K. So now this is the DSB thing. So what does DSB looks like in real time? Let's look at that's what the double sideband looks like in real time. So this will be the signal sent out to the antenna. That's DSB. Yeah, that's my DSB. Let's keep looking to mean. Yeah, that will be DSB. That's what the DSB looks like. Double sideband AM broadcast. Right now, it's still the same sound I was broadcasting. So still the same sound sent out through a 20,000 Hertz carrier. The next will be, what about Ssb? Ssb means we keep working. Instead of remove only the carrier, we will also remove the lower sideband, for example. So we will remove this part. We only keep half. Notice the upper half and the lower half is symmetric. So why we send out something symmetric? That means a waste of your bandwidth. First, you need to double the bandwidth. Ssb only need half bandwidth from here to here, 5K. The DSB still need 10K. So DSB is the same bandwidth as AM. AM is 10K bandwidth. DSB is 10K bandwidth. Started from 5 below and 5 above. So the Ssb only need 5K. So half the bandwidth. That's another advantage. Ssb, you can double the channels, double the amount of channel. So let's do the Ssb. Now we go to the same filter. Actually, same filter. All we need is increase this to, for example, 50K. All right. Oh, yeah, that will be DSB. Actually, I did the opposite. I should keep the upper side. So this is 20.1K. So this is still 21, but I will lower that to 0. Okay. Now it's upper side band Ssb. So if you look at the signal, so that's upper side Ssb. Notice the carrier is kind of, so this filter is not very good. So we will keep redesign the filter. Maybe change it to 2. Yeah, a little bit better. We already are the maximum order. Chebyshev and Butterworth, Chebyshev works a little sharper. So we keep the filter type 16th order because that's how my computer maximum order can realize. It will, instead of a band stop, I do a high pass filter. Let's do a high pass filter. It will be, not high pass, band pass. So I will do a 20K, 20.1K to 25K. So this will be the bandpass filter to keep the upper side band. Oh, bandpass filter. So that's results. Upper side band from here to 5. From here to 5. So it just started with 20, ended with 25. That's the upper side Ssb. Notice that we still have carrier. So this is called reduced carrier Ssb. This is one type of Ssb. This Ssb has a reduced carrier. The carrier is not as big as before. Before it's in the 1 watt range. Now it's 160 milli. So the carrier is reduced, but still there. It's called reduced carrier Ssb. This reduced carrier will help the receiver. Notice before I said the receiver will be more complicated, very difficult. Now with the reduced carrier, it's a little bit easier. We can keep reduce the carrier, remove the carrier by design a better filter, right? Let's do 3. Now we almost completely remove the carrier. So this is the upper side band from here to, let me see, we completely remove it. Not sure. We still have carrier. So it's very difficult to completely either using computer or using older filters. Very difficult to completely remove this carrier. But anyway, with more advanced filters, we can keep reducing this 20K here. So this will be the upper side band Ssb. Let's keep one more try. What we're doing here is keep increase where the passband start. That means the distortion for the human voice. So now 0.4K to 5K. So anything below 0.4K will be removed. Yeah, that's upper side band. So Ssb still have reduced carrier right here. Of course, we can look at this signal in time domain. So this is time domain. So that is the signal sent out to the antenna. Ssb signal, what the Ssb looks like. So when your transmitter is Ssb, AM transmitter, this is Ssb signal, RF signal goes to the antenna. Music is hidden here. It's up to the receiver to decode this signal, get the original voice back to the speaker. And it's a more difficult task compared with DSB. This is Ssb. Compared with DSB, it is even more difficult to traditional AM. Traditional AM being the easiest to decode, demodulate. We don't say decode. So that's the 5th topic. That's our demo. Let me stop this demo. By the way, you might be wondering what is this music sounds like. We can also hear it. We can hear this music. I forgot how to load it up. Okay, here. So I can load up this, open up this music, and we can listen to it. I recorded it last week from a radio station. It's a little song. So again, I have to load up this data to my instrument. This is wonderful because before, when we're using the real instrument, that's benchtop instrument, which costs thousands of dollars each, we still couldn't do this type of demo. And now this whole instrument total cost is $300. And it's so powerful. We can do all kinds of demos compared with before. So that's so this is the music, what it looks like. So we can play that music. And listen to it. Let's see. Hopefully it will work. This is the first time I tried. Earlier in the morning, I tried for a different class for something else. I'm not sure you guys hear it. Give me some feedback. You hear it? Anyway, I will work on that. This piece of recording music. The last topic for today will be number 6. So number 6 will be the last topic, will be the classifications of radio transmission. So this is a typical classification. It started with a letter, followed by a digit, number, and followed by a subscript. So if the first letter can be AFP, then followed by a number, then followed by some more detailed information. For example, if the video transmission code is A35, that means AM for voice, and F means carrier plus ppm modulation. So it's tell you a little bit the information about your station, either double side, full carrier, that's the conventional AM, double side no carrier, that's DSB, reduced carrier single sideband. So the last letter, subscript, tells you whether it's AM, DSB, or SSB. Also, if there is some modulation included, for example, this F means ppm, there's some modulation, so there's some coded message included for this AM broadcast. So A3F. Another example will be J3E, J. It's SSB voice, so J3E. So those are for our last. J is single sideband. That's a different standard designations. So J means a single sideband, 3 means analog, E means human voice. So our second code, what it means. So it gives you some reference to where to look for information. When you see some code like this, which with this table, 2 figures provide you enough information to get to know a little bit about your AM station. That's all I have for today. Well, Arturo, do you have any questions? We got only one show up today. I guess everybody's on vacation. I will stop the recording and, like I said, I will put it on Canvas and see you guys on Canvas.